This Zoom session is being brought to you by the fractal snow ring. Ooh, Irina Lee, just a moment. Irina Lee is in. Okay. All right, starting up. Okay, this is simple and damped harmonic motion. Harmonic motion refers to the ideal abstract case is a weight at the end of a spring, and how far is this displaced from its equilibrium point. And the idea is that when it's displaced from an equilibrium point, a force moves it the other way, and as a result, it goes up and down and up and down and up and down. So the height, if d is the height or distance, and t is time, then we have a sinusoidal motion. D equals a cosine omega t, or d equals a sine omega t. And of course, you could also have a phase shift, omega t minus phi. A is the amplitude, 2 over pi is the period, omega over 2 pi is f, the frequency. So it's 1 over the period. So for example, d equals 5 sine 3t. What's amplitude, period, and frequency? Amplitude is 5. Period is 2 pi over 3. Frequency is the reciprocal, 3 over 2 pi. You get a wave like this. All right. Now, realistically, there's going to be some friction on the wave. So it starts wobbling, but this friction, the wave dies out. So this is called a damped vibration. So what happens is you get an a cosine omega t, or a sine omega t, but there's also a factor e to the minus kt, a decaying exponential. All right, I'm not going to go over what frequencies or this or that. The book actually lists some really horribly complicated formulas. I'll not say it, bother with it. And if you do the extra credit, just use a calculator to get yourself a graph. So for example, d equals e to the minus t over 2 pi cosine t. Well, it's a cosine graph, but one that dies out like that. So that's pretty simple. Okay, I'm going to skip past this and move on to the next. Oops, chapter 4. I won't even bother. Oops. Oh, right. Have I, let me double check. Have I opened this up? I think I have. Let me double check. Have I opened up quiz 2? Yes, I have. So it, like everything else, is due by the end of the next week. So chapter 5.1. Here we get into polar coordinates. Rectangular coordinates are we plot a point at x by y. X is how far left to right, y is how far up or down. X or y are the horizontal and vertical distance. Each horizontal line corresponds to a constant value of y. Each vertical line corresponds to a constant value of x. I call this taxi cab space because this is how a taxi cab driver views the space of the city he's moving in, which street, which avenue. All right. Polar coordinates, this is how an air traffic controller sees space, seeing how far the airplane is at what angle from the control tower. Here we have a point is denoted by r by theta. So it's out a distance r at an angle from horizontal of theta. The circles correspond to constant values of r, and these tilted lines correspond to specific angles from horizontal to the right, from the positive x-axis. Now we connect these two with this diagram here. If we have a point at out a distance r at an angle theta over x and up y, we get a right angle triangle, and we get the usual equations. So x over r is cos theta, so x equals r cosine theta. Y over r is sine theta, so y equals r sine theta. So from r and theta, we get x and y, polar to rectangular coordinates. If going in the reverse, given x and y, to find r, well, that's Pythagoras. R is root of x squared plus y squared. Now, theta is a bit of a tricky thing because it depends on if you're on the right half of the plane when x is positive or the left half of the plane when x is negative. If x is positive, okay, y over x is tangent theta. So theta is arctangent y over x. That's on the right half of the plane with theta between minus pi halves to pi halves. On the other half of the plane, we have to add pi for a half rotation. And it'll be pi plus arctangent pi plus arctangent y over x. Because this angle here and it's a 90-degree opposite, it's 180-degree opposite, have the same tangent. So you have to, for an angle here, you have to add pi radians, which is 180 degrees. So given x and y, we'll get r and theta. So this is rectangular to polar coordinates. Some of your calculators may have a little button saying p to r and r to p, and that gives you polar to rectangular and rectangular to polar. So for example, if you have polar coordinates 3 out and pi over 2 around, what are the rectangular coordinates? Well, x by y is r cos theta by r sine theta. That'll be 3 cosine of pi halves by 3 sine pi halves. These being in radians, of course. And a little bit of computation, it's 0 by 3. Or polar coordinates 6 by 150 gives you what rectangular coordinates? Well, x by y is 6 cosine 150 and 6 sine 150 degrees. Okay, here they specifically specify a degree measure. And again, a little bit of computation. It's x is minus 3 root 3, y is 3. Here, if the rectangular coordinates are 1 by negative 1, what are the polar coordinates? Okay, since x is positive, we'll use the positive arctangent, arctan y over x. So root x squared plus y squared by arctan y over x, since x is positive. And this comes out to root 2 by negative pi over 4 radians. If the rectangular coordinates are root 3 by 1, what are the polar coordinates? Okay, the r value is root 3 squared plus 1 squared, which comes out to 2. Since x is positive, we have the arctan, and that'll be arctan of 1 over root 3, which is pi over 6, aka 30 degrees. Oh, that's right, yeah. Okay, that's pretty simple. Let's see now. All right, that covers this. Let me see if we can peek ahead to 5.2. Next time I'll go over using these identities, p to r and r to p, to convert polar equations to rectangular equations. And there'll be some examples such as this, and this, which turns out to be a circle, and this, which also turns out to be a circle, and these, which turn out to be straight lines, and these, which are more complicated shapes called cardioids, which means heart-like, or this, which is a 3-petaled rose. And we'll do some examples next time. Okay, I think that's it for today. We're going to be going up a little faster now, I think, just to go through the extra credit sets quickly. That's it for now. Questions, comments, requests?
On what day will you open?
Friday. I'm sorry, I can't hear you. Can you speak up a bit, or because I can't hear you?
Will you be opening the final?
I really can't hear you, and I doubt the others can. The question, if your question is when is everything due, Friday. So it's the quiz 2 and the homeworks 4 and 5 and the final. Oh, that's a good point. You know what? Let me do you a favor. All right, hold on. Just to make things faster. Let's see what we have here. Sorry. Let me just to give you a little more time on everything, I shall open up the final now. Bing and bing. A little early, but I don't mind. So, okay, you have a whole week to work on it. I think that's fair. All right.
Thank you. That's great.
It helps. I mean, these summer semesters go by so fast. So I might as well give you a little bit of speed up. All right. Other questions, comments, requests? Well, very well then. As Robert Heinlein said, a motion to adjourn is always in order. Is it seconded?
Thank you, Professor.
It is seconded.
Seconded. Yeah.
That's seconded. I shall see you on Monday.
Okay. Bye.
Thank you.
Bye.
Thank you.
Bye, everyone. Have a good weekend.
Ooh, what's this?
Hi, Professor.
Yes?
Is it okay if
I just submit my work on next Saturday and Sunday instead of Friday, or is that too late for you?
I'll let you do this if you promise not to tell anyone else, okay?
Thank you so much. Yeah, I just have a lot going on right now.
Stop, understood. Stop.
Okay, thank you so much. Have a good day.
Great. Amanda Snyder. Questions, comments, requests? And by the way, I'm glad to see you. It's been a while since I've seen or heard from you last. If you have anything to say, please speak up. Because in 30, if not, then in 30 seconds, we're shutting this down. Okay, good afternoon.